Okay, so one or two people asked me about this exercise. First of all, it's a very difficult exercise. All this stuff that we've been doing today is difficult stuff. It's at the end of the year 2 textbook. Now, just want to clear up one or two things because the answers aren't particularly helpful. I may even do full solutions to these myself, but to enable you to have a better go, I want to just point out one or two things. Now, it talks about finding the interval. That's just notation. We're not going to use an interval. We're going to talk about a range of values because we know we're going to solve these as inequalities. So that's all it's asking you to do. We want to solve the second derivative either greater than or less than 0, depending on which it is you try to find, and have the answer to the inequality as your answer to these questions here. Here, again, it talks about an interval. We're not going to do it like this and the way that the answers have done it. We're going to find the range of values that f of x is concave, and if the total range of values where f of x is concave encapsulates and sort of brings with it this interval here, then we can conclude that it's concave in that interval as well. Same with the convex. Point of inflection, we're going to solve the second derivative equal to 0, but maybe I didn't stress this enough. As we did in the example, you've got to show that it's a point of inflection by solving the second derivative equal to 0, but then also by substituting in a slightly smaller value of x and a slightly bigger value of x into the second derivative to show that you've got a sign change from concave to convex, and that's what a point of inflection is. Part 3 is the same, but you've got some tougher equations to differentiate and then differentiate again. If you've done the homework, by the way, or if you had a look at the homework, there's lots of good practice on doing the product rule, the chain rule, and the quotient rule. It's really valuable practice as well. So again, solve the second derivative equal to 0. You'll get some x values. Those will be the x values of the points of inflection, but you must investigate either side of the x values and show that there's a sign change in the second derivative. That's when you can properly conclude it's a point of inflection. Number 4, same again. Number 5, for a stationary point, we'd solve the first derivative, dy by dx equal to 0, to get the x value of the stationary point. Then you'd sub that x value into the second derivative to determine its nature. If it's positive, it's a minimum. If it's negative, it's a maximum. If it's 0, we need to put in values of x either side of the x value you found into the gradient function, because we're talking about a stationary point. And the values you get as the gradient either side of the stationary point will inform whether you've got a maximum, minimum, or a point of inflection. And that's like what we had in the example in the notes. Non-stationary points of inflection, you know that by now that we're going to be solving the second derivative equal to 0, finding what those points are, but also investigating either side to show that it's a point of inflection, because we've got a sign change in the second derivative. Right, so, sorry. Number 6, again, stationary point and its nature. You differentiate, find the stationary point, put the x value into the second derivative and determine the nature. Solve the second derivative equal to 0 to find the non-stationary points, and then you could probably cobble together a little sketch of that, but don't worry too much about that. 7, it's just really checking that you know what's going on. So I'll give you an example. Where is f-x positive? Well, it is positive at c, because c is an increasing function, or the function is increasing at c. F-x would be negative at a, and at b it would be 0. The second derivative, well, again at c it's going from steep to not as steep, and so the rate of change of the gradient is decreasing, so I would say f-x is negative at c. Okay, And then we've got some more of this. It's just getting a bit trickier with the differentiation, that's all, and the solving. But the principle is this, and I'll repeat myself again. Stationary point, solve the y by dx equals 0. The nature of the stationary point, you substitute the x value into the second derivative. If it's positive or negative, you know it's a maximum or minimum. If it's equal to 0, we need to investigate what the gradient is either side of the stationary point, and the shape of those tangents will inform us whether we've got, well, to which type of stationary point we have. Non-stationary point of inflection, solve the second derivative equal to 0, then investigate either side of that x value with the second derivative to show that we've got a sign change in the second derivative, because that will mean we've gone from convex to convex in that interval. Concave to convex, or convex to concave, I should say. Number 10, the mistake here is that he's not done the investigation. So the solving's all right. First derivative, second derivative equal to 0, x equals 5. If you substitute x equals 4.9 into the second derivative, or x equals 5.1 into the second derivative, you can show that there's a sign change in the second derivative, and therefore it's a point of inflection. Or not, as is the case in here. So that's the mistake. The student thinks it's a point of inflection just because he solved it equal to 0, but the reality is you need this backup check to check either side of the point of inflection, what the second derivative is, either side of the point of inflection, to verify that it is indeed a point of inflection. Alright, I hope that clears up some problems, but it's a difficult exercise. Just get what you can into me as soon as you can, probably tomorrow really. Get that homework done, because it's a long homework. I've been doing these solutions to it and it's really long. Okay, I hope you're all okay.